Hello there and welcome to the third movie in the Logic series. My name is Reductio and I work for Lonely Scholar. Today we will be talking about natural deduction, a syntactical proof system in logic. We will consider what is often seen as the most difficult rule in this system, the Reductio Ad Absurdum rule, often abbreviated as RAA. Reductio ad absurdum is Latin for reduction to absurdity. In general terms, it demonstrates that a statement is true because its negation would lead to something absurd. For example, one could argue that rocks have weight using a reductio ad absurdum argument. If rocks are weightless, we could infer that they fly in the air. But by this, we have reduced our assumption to something absurd. So our assumption must be false, and thus rocks have weight. In mathematics, our reductio ad absurdum is often called a proof by contradiction. One example is to prove that every number has a larger number. We can prove this by assuming the negation of our statement. Not every number has a larger number. In other words, there is a number with no larger number. But this assumption leads to a contradiction with the following truth statement. For every number we can find a larger number by adding 1 to that number. Thus, given that our assumption leads to a contradiction, it must be false. And our original statement, every number has a larger number, must be true. Now that we have seen two examples of the reductio ad absurdum, let's try to understand its role in natural deduction. A rule can always be understood in two ways, bottom-up or top-down. From the bottom-up perspective, the RAA rule says that we can prove P by showing that the negation leads to something absurd. That is, a contradiction. A contradiction is represented in logic by the falsum. From a top-down perspective, we can say that the RAA rule states that if we know that by making an assumption of the falsity of P, we can deduce a contradiction, then it must be the case that P is true. Okay, let's see how it works. So let's prove not Q implies P and not P until Q. That is, from our assumptions not Q imply P and not P, we have to prove that Q is the case. So we'll start off as always by writing the formula we have to prove, in this case Q, at the bottom. So this is a typical situation where we will have to use RAA. We cannot use an introduction rule because Q has no connectives. Nor could we obtain Q by using some elimination rule because Q cannot be found in our assumptions. We will have to use the RAA rule. That is, we assume the negation of our conclusion Q and try to prove that falsum is the case. So now we will have to prove falsum. A falsum can be understood as symbolizing the fact that there is a contradiction in our assumptions. For example, we can prove that rocks should be flying around everywhere, but we also know that they don't. In natural deduction, we can prove a falsum by using the negation elimination rule. The negation elimination rule states that if we have found two formulas that directly contradict each other, we may conclude falsum. But where to find such a contradiction? Note that in our assumptions we have formulas containing both P and formulas containing not P. So let's try to prove both P and not P. If we can do this, we have proven that there is a contradiction in our assumptions, and we may conclude falsum. The remainder of the proof is not that hard. Not P is one of our direct assumptions, so we do not have to prove it. But we will have to prove P. We can do this by combining our other two assumptions. We have not Q implies P and not Q. By using the implication elimination, we can now prove P. This completes our proof of not Q implies P and not P, until that Q. That movie helped you understand the Reduction Ad Absurdum rule. But before I leave you alone with the wonderful world of logic, I have two small, super free special RAA tips. First, RAA can be used to generate hypotheses. That is, if we're stuck at some point proving a certain formula P, we can always obtain an extra hypothesis, not P, by applying RAA and negation elimination. As you see, we will end up trying to prove P again, but we are in a slightly different situation than before, since we have this extra hypothesis, not P. Secondly, although it sounds nice to be able to generate hypotheses, often using RAA will only be confusing. As you can see in this example, sometimes using RAA doesn't get you anywhere, while using elimination and introduction rules will complete your most wished-for natural deduction proof. So use RAA only as a last resort.